This course module covers the technical fundamentals of ultrasonic level measurement. After completing this module, you will be able to recognize an application for ultrasonic level, describe how an ultrasonic instrument measures level, explain influences on ultrasonic measurement and how to compensate for it. Throughout the world, in a wide variety of processes, it's important to measure and control levels of a vessel. Of course, the level of these vessels have to be measured accurately in these applications. You can imagine the ultrasonic technology to be similar to the way a bat measures distance using sound. Metrologically, it's challenging to measure level using ultrasonic technology, because there are many conditions that can change the speed of sound. In this module, we will see the influence of the largest influence, namely temperature. Take, for example, a water treatment plant. Their task is to purify water and have it ready for distribution to a city or region. They supply fresh water to many families in the community. Within its process, this water plant must have accurate measurements of the water levels around the plant. The solution is to measure the process, for example using ultrasonic level instruments. The advantage of this method is that it can be done as a continuous measurement, and it does not have to be in contact with the surface being measured. With this, the manufacturer can ensure that the city had non-interrupted access to fresh water. Another example is commonly found in mining, cement, aggregates, and food and beverage industries. These plants store, process, and distribute dusty materials for use in the food we eat or as materials for raw materials used to build roads and buildings. Within its process, this plant must have accurate measurements of the silo and bin levels around the plant. The solution is to measure the level, for example, using ultrasonic level instruments. The advantage of this method is that it does not have any moving parts or mechanical components that require frequent maintenance. With this information, the manufacturer can ensure that materials reach their destination on time. To measure distance using sound, it's important to use the correct frequencies. I'd like to illustrate the use of the audio spectrum using a simple drawing. Here you can see that the typical human can hear frequencies between 20 Hz and 20 kHz. Medical applications also use ultrasonic technology, although at a much higher frequency. This gives them very accurate measurements, but is limited to a very short measurement range. For level measurement, we need to measure some large vessels, so need to use lower frequencies that can travel further. An ultrasonic level instrument works at the frequency just above human hearing capability. To measure distance, the instrument generates an ultrasonic pulse and measures the time until an echo is received. I'd like to illustrate how this pulse travels using a simple drawing. Here you can see how a sensor generates a pulse. This pulse travels to the target and then bounces back towards the sensor. Knowing the speed of sound, we can now calculate the distance to the target. On this slide, I want to go a bit deeper into how the ultrasonic instrument generates and measures the pulses. A microprocessor generates a pulse. This pulse is amplified to a large pulse. This electrical energy causes piezoelectric ceramic inside the transducer to vibrate, generating the sound. The sound bounces off the target and back to the sensor. The pulse, moving through the ceramic, generates an electric signal that is then processed further. This signal passes through a specially designed filter that eliminates all frequencies that are not of interest to us. The filtered signal passes to the processor, where an advanced algorithm selects the correct echo. In the previous slides, we observed the basic technical principle of ultrasonic level measurement. In the following slides, I would like to present the influencing factors of ultrasonic level measurement to you. Let's take another closer look at the principle of time of flight measurement. Using time of flight means our accuracy depends largely on our ability to know the speed of sound at any given time. The speed of sound is 343 meters per second at a room temperature of 20 degrees Celsius, or 68 degrees Fahrenheit, through air. Look at the graph to see the errors we can expect at a given temperature if we are not compensating for temperature. We can expect a 170 millimeter, more than 6 inches, error at 10 meters, 30 feet, if temperature is 30 degrees Celsius, 86 degrees Fahrenheit, and we did not compensate. That is why it is important to always consider temperature compensation when accurate measurements are required. Let us take a closer look at the sensor and what happens after we've pulsed. When we pulse an ultrasonic transducer, we are vibrating it to produce sound. When this pulsing has stopped, we require some time for the vibrations to stop. During this time, no meaningful measurement is possible and is therefore ignored in the measurement. This part is called the blanking distance and should be considered during installations. I now want us to look at an inherent property of ultrasonic waves. It is called the beam angle. Because we're working with sound, it's difficult to get the beam very focused. Typical ultrasonic instruments have a beam angle of less than 10 degrees. We use the term -3 dB beam angle, which refers to the point where the power is half of the full power. The result of this is that we need to consider obstructions in the beam's way. It means that for a 5-meter, 15-foot range, we need a clearance of about 30 centimeter, 1 foot, from the wall or obstructions to make sure that we get the most reliable result. Now let's summarize this learning module. What have you learned so far? Ultrasonic level measurement is used in many different processes to measure level. Ultrasonic level is measured by generating a pulse just above human hearing capability and measuring the time until an echo is received. The speed of sound is influenced by temperature, but is compensated for by ABB instruments. Every ultrasonic transducer needs time to settle after pulsing. This results in an ultrasonic sensor having a blanking distance. Ultrasonic sensors have a beam angle that needs to be considered during installation.